Let's begin our afternoon talks. Our first talk will be Anna Caraiani.
All right, well, thank you. So, so the goal for today is to actually start talking about perfectoid spaces and see some examples. But just to get started, I want to recall where I was at the end of the last talk and just make some comments. So what we had was X gamma, where gamma was a congruent subgroup of SL2Z. And so this was a modular curve. And so we were at the point where we wanted to understand the case of locally symmetric spaces that do have an algebraic structure. So really the case of Shimura varieties. So from now on, I'm going to work with modular curves, but just to remind you that, for what I'm going to say, kind of the end result is still going to hold true for a Shimura variety of Hodge type. If you know what that is, good. I guess it's in the notes. But for example, Ziegel modular varieties, which are Shimura varieties for the group GSP2G, or unitary Shimura varieties. So X gamma could be a Shimura variety of Hodge type. So those are ones that admit a closed embedding into GSP2G. So one example to keep in mind is GSP2G itself. And the other example to keep in mind is this U22 Shimura variety that was relevant for understanding SL2 or GL2 over an imaginary quadratic field. And maybe I'll point out it. For some things are harder to do in the higher dimensional case, and if we come to that, I'll mention it. And so where were we? We were at the point where we used this Borel-Serre compactification that was just a compactification of X gamma as a real manifold, and it was compactified into a real manifold with corners. And we were reduced to understanding. So the whole thing is really based on congruences. And so what we have to understand is the cohomology of the Shimura variety, say compactly supported, because we had Poincare duality, and with coefficients in Z mod P to the NZ for some integer n. Before I move on to talking about perfectoid spaces and, really kind of saying what we're going to do about this, I do want to make a remark. So there was a question yesterday, and I gave the wrong answer. So the question was, what if you, can you use other compactifications? Can you use a different one, not the Borel-Serre compactification? And here I really should mention this, namely that you can also prove theorems of this kind using the toroidal compactification, which is a compactification as an algebraic variety. And in characteristic zero, so for characteristic zero cohomology, this shows up in the work of Harris, Land, Taylor, and Thorne. And for torsion coefficients, this shows up in the work of Boxer. The difference is that in Boxer's work, somehow in order to understand torsion in the cohomology of arithmetic hyperbolic 3 manifolds, using toroidal compactifications, it's not enough to just look at this kind of cohomology of a Shimura variety, but really you want torsion in the coherent cohomology of the Shimura variety. But he has a method for dealing with this. So let me just mention this. All right. And now, so now I want to explain what to do about understanding this compactly supported cohomology. So in the kind of the Shimura variety, just singular cohomology using perfectoid spaces. And so the first thing is a comment about how you actually prove the result, because last time I talked a lot about how you use étale cohomology. The étale cohomology of algebraic varieties is a source of Galois representations, and that's how you construct them. And so in fact, in this setting, the way you understand the classes here is exactly not like that. So you don't look at étale cohomology. Instead, what you do is you use congruences. So this is kind of vaguely stated, but I think you should get a feel for what it's saying. So every system of Hecke eigenvalues, another thing you might remember from last time is, right, we don't want to understand all classes. We just want to understand sort of eigenvectors for simultaneous eigenvectors for all the Hecke operators, maybe generalized eigenvectors. So every system of Hecke eigenvalues occurring in this compactly supported cohomology of this either, say, modular curve or more general Shimura variety lifts to characteristic 0. So that's the key theorem that you prove. Well, I guess that Peter proves. So, and the remark is that, you don't actually, right, like to get the Galois representations, they are just constructed by congruences. So basically what you have here is a congruence of a system of Hecke eigenvalues that you're interested in with one that's a characteristic 0, 1. So the characteristic 0, 1s are already well understood using a generalization of what I talked about last time in the case of modular curves. So there you use étale cohomology, you use some analytic techniques, and you can understand the Galois representations here. And now for these, it's just they're constructed by congruences. And another remark is that, so I mentioned that this cohomology, so even for Shimura varieties, even for these algebraic things, in principle, there could be lots of torsion. So it's not saying that there's no torsion. It's just saying that there's a congruence to things in characteristic 0. So maybe another thing that might be interested in is that, when you construct this congruence, you may change the weight. So that means you may look at this cohomology with coefficients in some local system, not necessarily with coefficients in the trivial one. So weight may change, and the level at P, the gamma, the P part of gamma may change. But, you do get your Galois representations. So you can ask, about sort of proving a theorem where you can control these things better. And so in some cases you can do this, but just for constructing the Galois representations, we're going to lose track of the weight, and we're going to lose track of the level at P especially. So that's because we're going to use a perfectoid modular curve, and so somehow we're going to infinite level at P. Okay, so our goal for the rest of, I guess, the mini course is to understand the proof of this theorem, or understand kind of the main steps. I don't know, maybe I'll call it theorem star. So we want to understand this, and so I'll try to give you an outline, or just the strategy is to use perfectoid modular curves. So you go to infinite level at P. You use the Hodge-Tate period morphism, which is sort of kind of measures the relative position of the Hodge-Tate filtration when you have a family of elliptic curves, which is the sort of thing that you have over the modular curve. Since the modular curve represents a moduli problem of elliptic curves, you have the universal one. So I'll say more about this, but you use the Hodge-Tate period morphism. So maybe the goal for today is to talk about perfectoid modular curves, next time to talk about the Hodge-Tate period morphism, and then the last one is how you actually produce congruences. And so I'll maybe let's mention that the last step is to produce congruences. And if you've heard about the Hasse invariant, well, you can produce congruences using some objects that behave very much like the Hasse invariant, even though they don't have anything to do with the Hasse invariant. But this would be the topic of the last lecture. Okay. So the goal for today is to say something maybe about the first two things. So it turns out that the first two things are interrelated, and for that reason, so I want to focus on one, but I have to also mention two. Okay, and before we go to do that, to some extent, like in Bargov's first lecture, you want to, somehow the complex situation gives a guide or some intuition for what happens in the p-adic setting. So, p-adic Hodge theory is sort of inspired from Hodge theory. And in a similar sense, perfectoid modular curves, together with the Hodge-Tate period morphism, are sort of give a p-adic analog of the following complex picture. And so, I know, this stuff is more like heuristic or analogy. So we want a p-adic analog So again, we go back to the things that showed up last time. So modular curves, well, if you think of them as complex analytic spaces, so I guess as Riemann surfaces, they're covered by the upper half plane. And I guess you can think of the upper half plane as sort of an inverse limit of these spaces as your congruent subgroup gets smaller and smaller. And the upper half plane itself admits an embedding into projective space, one-dimensional projective space over C. And I'm going to call this embedding pi Hodge de Rham just to match the notation in the lecture notes. This is called the Borel embedding. But it's just the usual embedding of the upper half plane into projective space, into the Riemann sphere. It's called the Borel embedding, and it's a holomorphic map. So it respects complex structures. And another property that it has is it's equivariant for, it's equivariant for the action of our group. So I guess here our group is SL2 over Q, but the real points of the group act on the upper half plane, this symmetric space for SL2. And there's a natural, so you should think of this as a flag variety, parametrizing lines in a two-dimensional complex vector space. Okay. And if you think of it this way, there's also a natural action of the group GL2C on the flag variety. It just changes the position of this line. And so one important thing about this Borel embedding is that it's equivariant for the action of SL2R on the upper half plane and the action of GL2C on projective space. So I'll say this as the natural GL2C action on P1 restricts to the action of SL2R on H via Möbius transformation. So the one that we wrote down explicitly. And you can check that it really is, the natural one you would write on P1. And another important thing about this picture is that there's, in fact, a moduli interpretation. And again, so it has to do with Hodge theory. So I mentioned that the upper half plane parameterizes Hodge structures of elliptic curves. I mean, you have to think a bit about sort of different ways of describing the points here, but I mean, one way is to say that, well, elliptic curves are one-dimensional complex tori, and those are given by lattices in C, and the upper half plane sort of parameterizes the lattice, but the way that you give the lattice, you already give it with a basis. And so in that sense, what H2 parameterizes is an elliptic curve over C together with a trivialization alpha of the first singular homology. So you identify it with Z squared. So that's what you have here. And then I mentioned how X gamma, so depending on what gamma is, you may have a different moduli problem, but you always see elliptic curves together with some extra structure, a gamma level structure. And you have various examples of this. So, for instance, if you have gamma 0 of P for some prime number P, then the level structure is a subgroup of the P torsion of the elliptic curve of order P. But in any case, so this is what you have on this side. And then this Borel embedding, this map from the upper half plane to P1, you should think of this as sending the elliptic curve to just the Hodge filtration on the cohomology of the elliptic curve. So I guess in the notes, I refer to this as the Hodge-de Rham filtration just because, well, don't want to confuse it with the Hodge-Tate filtration. But I'll write it down. So the idea is this first homology, with C coefficients, if you tensor this up to C, well, on one hand, you have a trivialization. So this is trivialized, it's C squared. But then once you're here, you have a Hodge decomposition, so a direct sum decomposition. And you forget about the direct sum decomposition. You just remember the filtration part of it. And the filtration part of it you can remember as the surjection of this onto the Lie algebra of E. And so you can think about this map as taking E together with this trivialization to this line. I guess that's a quotient of C squared. If you work dually, you would see a sub. So a line in a two-dimensional complex vector space, which is what this flag variety parameterizes. Okay, so, right, like there's this moduli interpretation, and this is what we want to have in the p-adic picture as well. And instead of using singular cohomology, we want to use étale cohomology. And instead of this Hodge-de Rham filtration, what you want to use is the Hodge-Tate filtration. I want to make a remark before moving on, which is that, I mean, somehow even the complex picture itself is quite important in the theory of, say, Shimura varieties or, the study of automorphic forms. So maybe I'll just say that the above picture, so just the complex one, is used, say, for defining automorphic vector bundles, which are vector bundles whose sections are given by automorphic forms. So in general, if you want to define generalizations of modular forms and with arbitrary weight, you want them to be sections of certain vector bundles. These are going to be the automorphic vector bundles. And another thing that is expanded on in the notes is that, I mean, you should think of this as a period morphism. And if you want to make the notion of a Shimura variety precise, so you want to kind of, axiomatize the situation where the symmetric space for a group over Q is a moduli space of Hodge structures, what you need to do is you need to use the notion of a variation of Hodge structure. And in order to make that precise, you need to consider precisely period morphisms like this. So you have more general period morphisms, even in the complex setting, that show up in the notes. Okay, so this is a complex picture, and you can keep it in mind as motivation, but now we're moving on to the p-adic setting, maybe, 3. So I want to actually start with kind of the statement. We're going to make things more precise, but I want you to first know what we're trying to prove, and then I'll give you a hint of how we're proving it, and then we're going to expand, kind of find more properties and strengthen this result. But in order to make things so that you can follow sort of the higher dimensional case at the same time, I'm going to switch to the group GL2. So I'm going to take G to be the group GL2 rather than the group SL2, and that's because, I guess you could use GSP2G more generally, with G in Z greater than or equal to 1. So for G equals 1, you recover GL2. And then in general, the corresponding Shimura variety is a moduli space of principally polarized abelian varieties. So, okay, so this is going to be our group. And I'm going to have to also define various levels. So just need some notation. But so for, say, an integer m, we're going to define the congruent subgroups. I mean, this is easier maybe to say than to write down. Basically, you want some tame level, so some level away from P, and then you want to have full level P to the m at P. So I'm going to define this to be gamma P to the m. These are going to be gammas of the form something tame, so something away from P, at primes other than P, and something at P. And at P, it's a congruence condition, so congruent to the identity modulo P to the m. And then gamma sub P. And away from P, I don't know, in some level. We're not going to care about, for the most part, we're just going to fix it for the entire mini course. But some tame level, for instance, you might need this in order to not have stacks. Okay, so this is going to be inside GL2, Z hat, away from P. And if I write just gamma, this is going to be the 0 thing. Okay. And we're going to work throughout. Well, we want to have perfectoid modular curves, so we better work over a perfectoid field rather than just, say, over QP. So I'm going to take QP cyclotomic, which you've seen both in Jared and Kiran's lectures. So you take all pth power roots of unity, you join them to QP, and then you p-adically complete. And this has a ring of integers, ZP cyclotomic. Okay. All right, so talked about level and what field we're going to work on. So there's another thing that ends up being quite important and quite tricky in general, but for modular curves, it's not so bad. So we're going to work with compactification. So if you remember, the cohomology that we're trying to understand is compactly supported cohomology. And you can think of this as, say, the cohomology on the compactification of your object with coefficients in some j lower Schrieg. So I'm going to take x star gamma p to the m to be the modular curve of level gamma p to the n, but compactified. And the way you compactify it is just by adding cusps. In the higher dimensional case, this would be the so-called minimal compactification, that's singular. It's the one that we want to consider here. But for modular curves, we're just adding cusps. And now, let's see. So we have, well, what we want to prove is the following. Kind of two statements that are really sort of come together. They're intertwined. I'll say a word about why that is. But first, so there exists a perfectoid space. I'm going to call curly x star gamma p to the m. And this is going to be over, well, the spectrum, the adic spectrum of QP cyclotomic, ZP cyclotomic. But I'm just going to shorthand say that it's a perfectoid space over this field, such that, so we want to say modular curves at infinite level are perfectoid. So for that, we need to say that this is essentially the inverse, perfectoid, so I better take infinite level at p. Sorry, so not an m, but infinity. And I want this to be essentially the inverse limit of the adic spaces corresponding to these modular curves at finite level, where the finite level, the m, goes to infinity. So sort of the precise way to say this is to say that this perfectoid space is similar to the inverse limit of spaces at finite level. I'll say a word about this, but let me just, so you look at spaces at finite level, take an inverse limit with respect to m, and this is the adic space corresponding to x star gamma p to the m, but over this perfectoid field. So there's some subtlety about how you base change this to QP cyclotomic, but I'm not going to say anything about it, but you can read it in, say, Peter's paper. Okay, but so what do I mean by this similar to relation? Well, I mean, a perfectoid space is an adic space. So you have an underlying topological space, and you have, I guess, a structure sheaf and a structure sheaf with a plus. So on topological spaces, this relation is not so bad. So what you have is that the underlying topological space at infinite level is just the inverse limit of the topological spaces at finite level. And so, I mean, these are adic spaces that come from these smooth projective varieties. So these are quasi-compact. They're, as topological spaces, they're pretty nice. They're so-called spectral spaces, so homeomorphic to the topological space underlying an affine scheme. It turns out taking inverse limits also preserves nice properties. So as a topological space, this one is pretty nice. And by this equality, I mean there's a homeomorphism. It's a bit more subtle to say in general what you expect on the level of structure sheaves. So, I mean, if you were trying, to do this for affinoid things, and you had, so a tower of things, say adic spaces at finite level, and you wanted to say that this tower is similar to a perfectoid space, that would also be affinoid, and what you would need to do, say if you had, these were SPA of some Ri plus, what you want to take is the direct limit of the Ri's and then periodically complete. And that would be R, and this space would be SPA of R plus. So this is the sort of thing that you want to happen on the level of structure sheaves, but the way you want to do it is there exists an open cover of X star gamma p infinity by aphenoids SPA of AA plus, such that the direct limit, if you look at SPA of AI plus contained inside, well, maybe AM, it's more suggestive, inside X star gamma p to the m, where this is a direct limit over sort of, I don't know, spaces such that the map from SPA AA plus to finite level factors through these spaces. So this and direct limit of the AIs, this has a natural map to A, and you want this to have dense image. I mean, essentially what you're doing is taking the direct limit and p-adically completing. Thank you. Yes. Yeah. Okay, so that's the idea. And so I said I have two statements in this theorem, and the first statement is saying that essentially that the modular curve with infinite level at p is perfectoid. And the second statement is that there exists a map of adic spaces from this perfectoid modular curve to much simpler adic space, the adic space corresponding to P1. This is adic space over SPA QP, CP. And this map is the Hodge-Tate period morphism. I'm going to denote it pi Hodge-Tate. So there is such a map. And maybe under the first approximation, this map can be described on points as follows. This is coming from Bargov's lectures. So just like in the complex picture, you were mapping your, say, elliptic curve with a Hodge decomposition just to the Hodge filtration under the period morphism pi Hodge de Rham. Here, roughly what you want to do is on points, which are elliptic curves, you want to just look at the relative position of the Hodge-Tate filtration of the elliptic curve. Right, let me write this down. So let's take C to be complete, like in Bargov's talk, complete an algebraic closed extension of QP bar. So we could take the completion, CP. Right. So in this case, basically, we want kind of a moduli interpretation of the Hodge-Tate period morphism that's similar to what we saw in the complex picture. So I want to talk about, say, COC points, if you want. And so we have our ground level modular curve. And this parameterizes, say, elliptic curves plus some gamma level structure, which I'm just going to mostly ignore. This is always tame level. Maybe we want to look at X star, the next step in the tower, gamma p. So here we're parameterizing, well, still elliptic curves, but now, still the gamma level structure. But now we also have a trivialization, so full level, means that you trivialize the p torsion in the elliptic curve. Identify it with z mod pz squared. Okay, so this is one step. You keep going up the tower, you have p to the m and so on. At infinite level, you should think of this as and of course, I have compactification, so you also need to think about Tate curves, but let's not talk about them. So here you still have your elliptic curve, your gamma structure, level structure, and a trivialization of the whole Tate module of the elliptic curve. Okay, so I've sort of built myself into a corner here because I don't have room for the Hodge-Tate period morphism. So maybe, okay, it's good that you can see more slides simultaneously. So I have the gamma, so x star gamma p infinity. And so here we have E together with alpha. Here, say ground level, we just have E. And now this goes to P1, adic, otherwise, I don't know, it might be confusing. The Hodge-Tate period morphism is here. And then the point is that E and alpha should go to the following. So the Lie algebra of E, tensor over C, just Tate twisted, is a sub inside TP of E, tensored over ZP with C. And alpha trivializes this, so it's just going to be identified with C squared and under alpha, and the Hodge-Tate filtration is just given by, well, this sub and then the corresponding quotient that you saw in Bargov's talk. So the idea is that such a point goes to this line inside C squared. Okay. All right, so this is Hodge-Tate filtration. Okay, so I want to, so just maybe to recall it, it's 0, goes to Lie, algebra of E, Tate twisted, goes to the Tate module, goes to the Lie algebra of E dual. This is one of the forms that Bargov wrote down yesterday. And one comment that I want to make that also Bargov made, but I don't know, I want to emphasize it, because we are really dealing here with a relative situation where we have a moduli of elliptic curves. So really we have a universal elliptic curve over this space, is that you really, so over individual points you have a direct sum decomposition. But if you want to make this work in families, you really need to think of it as a filtration. And so you can just sort of, like the thing that varies continuously is this line. You cannot split it canonically in the relative setting. So this is, the Hodge-Tate filtration is not split. So it's really natural to think about the filtration rather than the decomposition. And another comment that's related to this is, so in order to see the Hodge-Tate decomposition, you cannot just look at the Tate module. You need to tensor with this field C that basically contains the periods of elliptic curves over C. Well, okay, it contains the period of the elliptic curve E. So somehow it's similar to what happens in the complex setting, where in order to see the Hodge decomposition, you need to tensor singular cohomology so your coefficients should go from Q to complex coefficients. So if you want to do this in the relative setting, then somehow you need to kind of go over a base that's even bigger. And it turns out what you need to do is work with an affinoid perfectoid cover of your modular curve, say even at ground level, so x star gamma. And so to define the Hodge-Tate filtration in the relative setting, need to work over an affinoid perfectoid cover. And you already have a universal elliptic curve at this level, so you can already ask about the relative Hodge-Tate filtration here, but you cannot see it unless you sort of look over an affinoid perfectoid cover. And so somehow this is why the two parts of the theorem, so the fact that the modular curve with infinite level at P is a perfectoid space, and the existence of the Hodge-Tate period morphism are interrelated, because you can see this Hodge-Tate period morphism that measures the position of the Hodge-Tate filtration in the relative setting. You can see it because this is a perfectoid space. So, you define, in order to define this not just as a map on points, but as a map of adic spaces, you could just take an open cover of x star gamma p infinity by affinoids, and then locally you can define your map. So that's why you need to know that this is perfectoid in order to see the Hodge-Tate period map, and sort of conversely, somehow in order to show that this is perfectoid, it turns out that you need to use the group action. So at infinite level, the modular curve has an action of the group GL2QP. And you can think of the group just acting on the tower, some, by Hecke correspondences. And you need to use this action to translate the perfectoid structure around and cover the entire space, the entire topological space corresponding to x star gamma p infinity. So, 1 and 2 are sort of proved at the same time. And if you find some perfectoid structure here, and you move it around, and that also allows you to move around the Hodge-Tate period map. And so maybe another thing to say, we're going to talk more about it tomorrow. You also have a natural action of GL2QP on this flag variety. It's just flag variety parametrizing lines, so GL2QP changes this line, moves it around. And another thing that's important about the Hodge-Tate period map is that it's equivariant with respect to this group action. So the same thing that you saw with Möbius transformations and GL2C in the complex picture also holds in the p-adic picture with the action of the group GL2QP. But we're going to talk more about the properties of the map tomorrow. Maybe just to summarize, somehow 1 and 2, are deeply intertwined of the theorem. Okay. So, right. So maybe my remaining time, what I want to do is just so the tower, you always have a, that's a good question, sorry. I should have maybe said, let me take this one. So on the tower, you have this sort of trivialization of the p torsion. And you can see an action of GL2, of ZP here, right. But somehow, it's Hecke operators. So you can still, you can rewrite, maybe you should see this in the notes, actually. So you can rewrite the moduli problem as a moduli problem, say, for elliptic curves up to quasi-isogeny, instead of a moduli problem for elliptic curves up to isomorphism. And if you do this, then you can also define an action of GL2QP. And you precompose your level structure with this action of GL2QP, and that's how you get it. So from the moduli point of view, you have to switch from up to isomorphism to up to isogeny. And then more generally, whenever you have a locally symmetric space, you do have an action of GL2QP, or the p-adic points of your group. If you take the inverse limit with the level going to 0, for that you don't think of the moduli interpretation, you just think about the definition of the Hecke operators. So maybe as an exercise, think about how you define Hecke operators and try to see how that gives you something on the tower. Sorry, I'm worried that I'll get something wrong if I just try and write this out now. But, okay. So, right. So what I want to do for my remaining time is say something about where the perfectoid structure comes from. And this goes back to maybe some examples that you've seen in Kiran's talk. So one way to produce perfectoid spaces is to start out with, say, a formal scheme and keep taking p-th power roots, and then take an adic generic fiber of that. So we're going to consider, say, xn, maybe, so an infinite tower of formal schemes. I'm going to call this F1, F sub n, be a tower of flat formal schemes over the ring of integers in QP cyclotomic. And we're going to assume that the maps Fn, when you reduce them mod p, are the relative Frobenius. So maybe factor as xn, you reduce this mod p, you have the relative Frobenius just to xn tensor CP cyclotomic, same thing mod p. And then an isomorphism with what you see at level n-1 in the tower. So relative Frobenius and isomorphism xn-1 mod p. So assume that you have something like this. Then you can form the inverse limit in the category of formal schemes of the xn's so over this SPF ZP cyclotomic. And this inverse limit, so if you take this, this gives the generic fiber x infinity. So take the formal scheme, turn it into an adic space, and then look at the generic fiber of that adic space. So it gives this, which is a perfectoid space. Over QP cyclotomic, and moreover, which is similar to, in the sense that I explained earlier, to the inverse limit of the adic generic fibers of the schemes xn. Adic generic fiber of the formal scheme xn. And so a concrete example of this situation, where you start out with affines, is the following. You've seen it, but I don't know, maybe this is bit much, so it doesn't hurt to see it again, is you take each xn to be just, you look at this algebra in one variable. So all the xn's agree, and the transition maps just correspond to sending t to t to the p. So the transition maps take pth power root of the variable t, and then this gives x infinity SPA QP cyclotomic, Tate algebra, T ZP cyclotomic. 1 over p infinity. Right, I claim that this is a, right, so this is an example of a perfectoid space that you've seen, and you can get it from this tower of formal schemes where transition maps are Frobenius mod p. So what we want to show is that part, maybe I'm out of time, so maybe let me just say that we'll show, am I out of time? Am I correct about this? We'll show that a part of x gamma naught p to the m, m has this kind of behavior where gamma naught p to the m is the same thing, matrices as before, but at p you have a congruence just to upper triangular things, mod p to the m, maybe determinant 1. Okay, so the first thing to do is to show that you have an intermediate level structure where you have a tower or a partial tower with exactly this kind of behavior. So I'll talk about that next time.
Questions for Anna? Where?
I guess this is just a small technical question, but is there any reason why we require this formal scheme to be flat?
That shows up, yeah, if you want to define something perfectoid, what you need is some notion of, what is it, almost perfectoid algebra, like for an integral thing, and flatness is a condition that's part of this. So yeah, we need that.
So I have a question.
Sorry.
Can you say something about the role of QP cyclotomic in all of this versus some other perfectoid field? Started out over QP cyclotomic.
Sorry, yeah, I started, well, I guess because you want to work over a p-adic field, a perfectoid field.
Right, but why that one?
Why that? I guess, so one thing is, like, if you look at level p to the m for a fixed m, then you have somehow in the moduli problem of what you're parametrizing, there's a Weil pairing that naturally gives you a way of seeing the modular curve at level gamma p to the m as a space over, say, spec qp adjoined mth, like p to the mth roots of unity. So in that sense, I guess it's, yeah, you should think of the modular curve as living over this. And so the tower of modular curves should be a perfectoid space over QP cyclotomic. So it comes from the Weil pairing on an elliptic curve that gives you p to the mth root of unity if you're looking at p to the m torsion.
Do you actually need some of these sort of finer properties of integral models that like have reduced special fiber, for example, over?
You need some properties of integral models, but this is something that works for Ziegel modular varieties. So it's somehow you get away with having an integral model at finite level with understanding the ordinary locus there, and Yeah, maybe, I mean, yeah, maybe that's all you need in terms of integral models. So I'll talk about it next time. I mean, I intend to say what you need, but yeah.
Great,
It's
thanks.
Yeah.
Can you go to any extension which contains QP cyclotomic?
Sorry, maybe, right, the question is whether you can go to an extension that contains QP cyclotomic. Well, I guess once it's perfectoid over QP cyclotomic, you could base change it to, say, C, where C is this complete algebraically closed extension of QP. I guess the point is that, I guess the first time you see this is on QP cyclotomic.
All right, let's thank Anna again.